Okay, today we're going to talk about Unit 10, Lesson 5, which is discussing the effects of dimension and area changes. Okay, basically what it comes down to is if you change the dimensions by a certain ratio or factor, then that will change the area by a corresponding factor. So let's take a look and see what's going on with this. Okay, here we go. It starts, it says, consider the area of an original triangle with base B and height h. Okay, so as you know, the area formula for a triangle in its basic form is 1/2 of the base times the height. So this is a diagram showing you this. What they're going to do is they want you to find the area of a new triangle whose base is twice that of the original triangle and whose height is 3 times as much. So this is what we're going to do. First, we're going to draw a diagram of our information. So this says that we change the base by 2, so related to the first diagram it's 2b and the height is changed by 3, so instead of h we have 3h. So we're going to use our formula to help us with this. So this gives us the area of the new triangle is equal to 1/2 of 2b times 3h, which is equal to 1/2 of bh times 6. Now the 1/2 of bh, what you're going to see here is that's what the original area was. So the area has changed by a scale or by a factor of 6, which is the 3 times the 2. This is because this is a linear formula. So because the linear formula doesn't have anything else going on like a squared term or something like that, then this gives us that it's simply 6 times as much as the original area. Okay, so this leads to a generalization concerning the new area. The new area is the old area multiplied by the product of the factors by which the two dimensions of the old area changed. This is true for most polygons we have dealt with. However, this formula needs adjustment for some special cases as will be seen shortly. Okay. First place that's going to happen on things that have stuff like a circle where you have the radius squared and that type of thing is what generally affects that. Also, it's going to get into things like the trapezoid, which means that you take the arithmetic mean of the two bases to find what you got. So anyway, but let's take a look at this. Example 1, if the area of a triangle is 36 centimeters squared, what is the new area if its base is increased by a factor of 4 and its height is only half of its former value? Okay, so we do what we did a while ago. We take the two factors, 4 and 1/2, multiply them together because that's what's going to happen to those two quantities, the base and the height. So this gives us a net change of 2. Okay, so we take the area of the new is equal to the area of the old, which was 36, times the factor that we just found, which was 2. So the new triangle will have an area of 72 square centimeters. Okay, example 2, a parallelogram having an area of 100 square feet is shrunk so that its base is only 1/3 of the original base, while its height remains constant. So what is the new area? Okay, so here's what we got. We got 1/3 is the new base times the 1 because the height stayed the same gives us a net change of 1/3. So we put it in. The area of the new is equal to the old area of 100 times 1/3, which gives us 33.3 repeating square feet. Okay, so now we want to think about something that's a little not quite as straightforward. It says that you consider changing the area of a trapezoid by changing the size of just one of its bases. Okay, so draw the situation that we got. So you start out with a trapezoid. You have two bases, B1 and B2, and you have its height. Okay, so all that we changed here is that we changed B1 by a factor of 2. Okay, so our area formula for the trapezoid is B1 plus B2 divided by 2 times the height. So our new area is going to be 2B1 plus B2 over 2 times the height. So that's going to be how that would be how we would figure it out. We would simply plug in the values of it and we'd see what change we got. So you'd see here that it's gonna change some, but it's not gonna be changing quite as linearly as what we've been doing. So let's take a look. Notice that the new area is not changed by a factor of 2. If both bases had been changed by a factor of 2 with the height remaining the same, then the new area would have been twice the original area. So once again, here's what our situation is, or this is what it would have been if we did that. So that the first trapezoid has an area of B1 plus B2 over 2 times the height. The second trapezoid has an area of 2B1 plus 2B2 over 2 times the height. So this means we can factor a 2 out of the numerator, put it out front, so we have 2 times B1 plus B2 over 2 times the height. Okay, so this leads to a modification of the rule on page 1 for finding the new area when dimensions change. When the area of any plane object is the product of two quantities, then the new area is the old area multiplied by the product of the factors by which the two quantities of the old area changed. Okay, notice for the trapezoid that one of the quantities is B1 plus B2 over 2. If the area of a trapezoid is 80 square inches, what is the new area if the lengths of both bases are increased by a factor of 6 and the height is only 1/3 of its former value? Okay, so we start out with our formula, which is B1 plus B2 over 2 times the height. Plug in our scale factors, which changed. So B1 plus B2 over 2 changed by a factor of 6, and the height changed by a factor of 1/3. So when we multiply those together, we get a net change of 2. Okay? So this is where they came from. So now we're going to use the 2 because the area of the new trapezoid is going to be equal to the old area, which was 80, times what we found was the net change, a factor of 2. Okay? So that gives us the new area is 160 inches squared. Okay, example 4. A regular hexagon has an area of 25 square meters. What will be the new area if the perimeter is increased by a factor of 4 and the apothem by a factor of 2? Okay, if you remember, the formula we've been talking about earlier in this chapter was that the area is equal to 1/2 of the perimeter times the apothem. Okay, so we simply plug in our changes, which is going to be 4 times the perimeter and the apothem by a factor of 2, so that gives us 4 times 2 equals 8. Okay, the 4 came from the perimeter change, the 2 came from the apothem change, and 8 gives us our new factor. So the area of the new one is going to be 25, which is the old area, times 8. Okay, and the 8 just simply comes across like this. That gives us that the new area is going to be approximately 200 square meters. Okay, example 5. A congressional district in the shape of a rhombus originally had an area of 250 square miles. If the area is increased to 500 square miles by increasing the length of both diagonals by the same factor, what is that factor? Okay, we can work backwards with these formulas just like we did earlier when we were going the other way. So what we're going to do is take this. So the original area is 1/2 diagonal 1 times diagonal 2. So we put in our factors. So we want f and f because we're looking for that. So f times f is equal to f squared. Okay, 1f comes from the first diagonal, 1f comes from the second diagonal. Okay, so the area of the new is equal to the area of the old times this factor f squared. Okay, so we plug in our information. Our new one is 500 square miles. Our old one was 250 square miles. So this gives us f squared times 250 is equal to 500. Divide both sides by 250. So 2 is equal to f squared. Take the square root of both sides to solve it. So the square root of 2 is equal to f. So the scale factor is approximately 1.414. Okay, example 6. When considering the areas of two similar polygons whose sizes differ by a scale factor of SF, our scale factor, that just represents it, the areas will differ by the value of SF squared. So you square the scale factor if you have similar polygons, and only if you have similar polygons. Okay? So we do this. The scale factor of polygon 1 to polygon 2 is 3. If the area of number 1 is 27 square meters, what is the area of number 2? Okay, so the scale factor of 1 to 2 is equal to 3 to 1, and the scale factor of 2 to 1 is equal to 1 to 3. So it just depends on which way you're going with this. Okay? So what they said is if the area of number 1 is 27 square meters, what is the area of number 2? So we can see from what we just did up there a minute ago that that polygon number 1 is larger because it's represented by the 3 in the ratio. Okay, so the area of the second one is equal to the area of the first one times the scale factor of 2 to 1, which is 1 to 3, squared. Okay, so the area of the second one is equal to 27, which is our original value, times 1/3 squared is equal to 27 times 1 over 9, which gives us approximately 3 square meters, or actually exactly 3 square meters. Okay, this pretty much concludes this lesson. Once again, if you've got any kind of questions about this, make notes as you go along. Go back and find where you had the problem with it. If you didn't do so, bring that to class tomorrow and ask your question, and we'll do those before we actually start any work on this. Thank you very much. Goodbye.